Okay. All right, page 41 is our Chapter 20 notes, Part 3. It's not going to be majorly lengthy. We're going to go over a couple of things, one new thing today. All right. Now, your homework will be not the entire Chapter 20, Part 3 homework, okay? So homework-wise, I'm going to shorten it to just pages 45 and 46. Okay, 45 is a phantoms model. That covers something new we're learning today. And then 46 is the warm-up because we're quizzing on Monday. Yes? Yep. Okay, so here we go. So we know that we've got the definition of p-value, but I want to talk that through with you through one-tailed problems versus a two-tailed problem. Everything we've had so far has just been one-tailed. So, for example, all our alternatives have just been either a less than or a greater than. So if we had an alternative where our p was less than a particular percent, okay, then what kind of tail would that be that we would be calculating the p-value for? Where would be more extreme? The probability of getting this sample or something more extreme, which direction is more extreme? To the left. Okay, good. So our p-value is this shaded area down here, and that's one tail. So it would just be that one set of values. Okay, if we had an alternative where we are wondering if something is actually greater than that hypothesized value, that hypothesized percent, then we would be getting most likely our samples up here, and then of course more extreme would be in which direction? Our p-value would go which way? To the right. Very good. Okay, so then that one tail's worth of shaded area is the probability that is our p-value. Okay, but now we're going to talk about how you handle a problem that is two-tailed. A two-tailed problem comes from an alternative hypothesis or a question where you're just wondering if the results are significantly different than what you have hypothesized. So if you say, the company is producing ball bearings that are at 6 millimeters, is the average significantly different from 6 millimeters? I didn't indicate a direction. So if we were doing a proportion problem, we would say P is not equal to a particular hypothesized proportion for our proportion problems that we're going to do in this chapter. Okay, so in that case, here's how this works, because you will only be given one sample. So let's say that the one sample that you got was a lower sample. Okay, so let's say the one sample you got was a lower sample. Which direction is more extreme? Left. Okay, so we would compute this area down here, but this is not our total p-value for this problem. Okay, our total p-value comes into play when you basically mirror image this and you are saying, okay, the upper tail is the same amount based on that sample. So these two tails together make up the total p-value. Okay? So for a two-tailed problem, you have to total those up yourself. Okay, so what will I do? Because when I get my computing and I do my norm CDF to compute this lower tail area, how do I then get the total value? If I just know that lower area. Take that value and do what with it? Multiply it by 2. Very good. So to get that total, you're going to take your one tail that you computed, multiply that by 2, and that will give you your total p-value. Okay, so that's the one thing that you have to remember, is that if it's a two-tailed problem, when you get your one p-value, your one area that you compute, that's only half, multiply it by 2 to get the total. Okay, and so again, p-values are the shaded area. They are that probability of getting that sample or something more extreme if the null is true. Let's review that we know our alpha is also a shaded area. It's the size of the rejection region. Okay, so when they tell us, when they dictate to us an alpha, then we know we're going to compare our p-value shaded area to the alpha shaded area like we discussed yesterday. Okay, so let's move on and let's do one of these kinds of problems. And we're going to write it on the next page where I don't have a Phantoms model template drawn out for you. So we're going to do the problem without the Phantoms model all written out there, and so we'll kind of go through making sure we remember what PHANTOMS stands for, because the template's gone. Okay, so from now on out, including your quiz on Monday, you're not going to be given a template with all the little hints of what to do. Okay, I wanted to fix this problem so it's a test. So here we go. This is a problem where in a 2001 National Vital Statistics report, it was indicated that about 3% of all births produce twins. Okay, so we know overall twins are produced at a rate of 3%. Data from a large city hospital found 7 sets of twins were born to the 469 teenage girls that were pregnant. Running an appropriate hypothesis test, do that to determine if, so you'll have to write this in here because I changed the problem, determine if the rate of twins born to teenage girls is different than the overall twin rate. Okay, so let's determine if the rate of twins born to teenage girls is different than the overall twin rate. Okay, so we're going to go to the next page, and I don't like the problem that I have there. I decided to change it. I just really like this twin problem. So kind of scratch that out, and we're going to do the twin problem. You know, we're going to be doing our PHA, our phantoms over there on, you can write phantoms over there on the left if you want to, if that'll help you remember what all you have to include. Okay. All right, so now I'm going to let you do some of these things, and so we'll do it a little bit at a time. I'm going to stop or pause and let you do P, H, and A by yourself. We'll check them, and then we'll go on. So what does P stand for? Your parameter that you're defining, which in this case is a proportion. H, what does H stand for in the Phantoms model? Your hypothesis statements. Very good. What does A stand for in the Phantoms model? The assumptions. So that's when you write out your get real and your random, independent, large enough, normal model and stuff. All right, so take a moment, do PHA, and we'll check back on those 3 items. Okay, let's check and see how you did on those so far. Check some of the details. Okay, so you are checking out something about, you're trying to make a claim about teenage pregnancies and the rate at which twins were born. So I said that P equals the proportion of pregnant teenage girls who have twins, or the proportion. Make sure that your denominator is the teenage girls, the pregnant teenage girls or teenage pregnancies. Don't say proportion of twins born to teenage girls. That sounds like you're doing, well, proportion of twins sounds like twins is your denominator. Yes? Correct. Okay, so this problem gives you information about all births. It says 3% of all births have twins. Okay, so then you're going to look at a subgroup of teenagers and see if the teenage subgroup is the same as the overall rate. So what you are making a claim about, what this test is about, is teenage birth rates to twins. So this problem is about teenage. Correct, that's your hypothesis. So see, your null hypothesis, let's start off saying teenagers rate's the same as overall rate and see if we have evidence against that. Okay? So we start off saying with your null hypothesis that the teenage pregnancy twin rate is the same as overall. And then we're going to see if the sample we get gives us evidence to reject that and say that the teenage rate that of twins born to them is different. Okay? Yes, ma'am. Oh, we marked that out. So you just kind of like missed that information. Yeah. Here's what we changed it to. See? We marked out that little thing there and yeah. Okay? All right. So back to this. Okay, so there's your null and your null and alternative hypothesis. Okay, now let's do check assumptions. We are saying that, what's our first one? Random what? Yes, and these are randomly selected teenage pregnancy cases. Okay, because this is about, I'm collecting data on teenage pregnancies. Okay, so I've randomly selected teenage pregnancies assumed. And this is kind of a big assumption. You know, it tells us about a hospital and that they were all taken from one hospital. Maybe that was a cluster. Maybe they randomly selected that cluster and then took all of the teenage ones there that year. And they say it's like all cases. I don't know. So we're assuming that's random. Okay. Independent, we're assuming that the 469 is less than 10% of all such teen pregnancies. Not all pregnancies. Not all pregnancies. We're talking about teen pregnancies. Okay, and our large enough. Okay, make sure that on your large enough, you are using this true P right here. 469 times 0.03. I have had to redo answer keys over and over because sometimes I have a tendency to put P hat there, but we have true P. That's the hypothesized P. Yes, ma'am. So the question is it pregnancies versus births? And so, sorry, I just kind of interchanged those and made an assumption that the pregnancies will result in successful births. So, sorry. I guess I should be more specific about that, but okay. I guess we're assuming that when we have a pregnancy, it goes to term and we have a birth. Yeah. Even if it is early pregnancy termination. Okay. So I was using those interchangeably. Okay. So our normal model applies. All right. So that's P, H, and A. N is the next thing in the phantoms model. Phantoms model. N in the phantoms model means to do what? Name. So that is a 1 proportion Z test. Is what we're going to be doing. A 1 proportion Z test. Okay, so P-H-A-N-T. T is telling you to get your what? Yes, your test statistic, which is our Z-score. Okay, very good. So I want you to compute that. Let me give you a few moments. I want to see if you can compute that correctly. So get your standard. Okay, so let's check your numbers. Now, let me tell you the thing that I frequently boo-boo, and I've had to, again, make many new keys because I'm real bad about, because I'm just so tempted. I mean, I just wrote this P hat is 0.015, and so then I'm just kind of going through the motions, and I don't think about it, and I put 0.015 here. It's not what goes there. P hat is not what goes there if you have true P. And in the hypothesis test, we have a hypothesized P that we use there. So make sure for your standard deviation, you used that 0.03, not the p-hat. Okay, and so then our z-score was made from p hat minus your p over your standard deviation of p hats, and that's negative 1.9. So essentially, we are saying, if you look at this picture I have drawn here, that we got a sample down here at 1.9 standard deviations below the mean, and so that one, to get the p-value of that, so how would I get the p-value of that sample? Norm CDF, which direction? To the left. Okay, so to get that one tail, I'm going to norm CDF to the left. So I norm CDF to negative 99 to negative 1.9, and I got 0.029. Okay. However, this is a two-tailed problem, so just one tail is not enough. To get the total of both tails, I have to multiply it by 2, so the total p-value that I'm going to use to compare to alpha is 0.058. Okay, so let's see, that was obtain a p-value and compare it to alpha, so that compare that to alpha. What do you get? Or we'll use a default alpha of 0.05. So then what's your conclusion? What decision are you going to make about your hypotheses? Good. You will fail to reject because you can see that your 0.05 is greater than alpha, so therefore you failed to reject. Yes, ma'am. Because the question was, the reason you know it's two-tailed is because the question was, is there a difference? Is it now different? It didn't indicate, is the teenage rate lower or higher? It said, is it different from overall? And then because it said, is it different overall, I did a not equal to sign here. That's what indicates to me that it's two-tailed. Sometimes it'll say, is it the same? Sometimes, is there a change? It just won't really indicate to you one direction or the other. Okay? Is it as precise? You know, you don't really know what they're talking about direction-wise. Okay, so now let's do our conclusion. State our conclusion, and that starts with an S, and we say first off what? Since the p-value is greater than alpha, and you don't have to put those numbers in there since it's just a line above. Since the p-value is greater than alpha, and then my conclusion, my decision, failed to reject. Now, let me give you a hint of a strategy of how to do this. You are failing to reject HO. And at that point, I want you to visually go up to the top, and instead of writing HO, don't write HO, you have to write it out. Boy, that's bad going over that. Instead of writing out HO, you write it out in words. So I fail to reject that, and I come up here and say, the proportion of pregnant teenager girls who have twins equals 0.03. Okay, so I'm regurgitating that null hypothesis. So I go directly up there to the top and look straight at that and rewrite it instead of the symbol HO. And so that's how I have done my conclusion here. I failed to reject that the proportion of pregnant teenage girls who have twins is 0.03. And then there's one more thing I say. It's about if I have evidence or do not have evidence of the alternative. It's the statement about the alternative. So let's talk about it. I didn't reject the null. Am I saying the null is true? Am I saying the null is true? No, I'm not saying the null is true. I just didn't have enough evidence to reject it. So can I say, is the alternative true? No, it is not. I didn't reject the null, so I'm not going ding ding ding. I got my alternative is true. So I have no evidence of HA. I didn't get enough evidence to say the HA is a go. So that's the end of your conclusion. No evidence that P is not equal to 0.03. Okay? All right, so that's the conclusion of exactly how you do that. That's another example of a phantoms model. Hopefully you're going to be able to do that without a template now. And so again, your assignment is page 45, which is a phantoms model, and then page 46, which is the chapter 20 warm-up, because you are having a quiz on chapter 20 Monday.